Okay.
Good morning, class. Go ahead and take out your books and turn to page 62. We're going to be continuing talking about kinetic theory and going over how gas pressure and things like that works. So for review from last lesson, what does kinetic theory state? Emily?
Gas molecules are continually moving about and colliding with each other and with the surfaces.
Correct. Gas molecules are in constant motion, but how are they moving? What path are they following? Tim?
A straight line path.
Correct. As they move and bounce around the room, they're never going to be curving or moving. It's always a straight line path. What type of collisions do gas molecules undergo? Abby?
Elastic collisions.
Right, and that means that as they move around the room, they're never going to lose energy. Every time they bounce off a wall, bounce off the floor, bounce off of you, they keep their energy, unlike inelastic collisions, which lose a little energy every single time they bounce into something. If I was to heat up a gas, would the gas molecules move faster or would they move slower? Emily?
They move faster
Why would they move faster?
because the kinetic energy of a gas molecule is directly related to the temperature.
Right. So why don't we have to take into account the gas molecule's individual volume when we're working with a gas? Abby?
Because they're so small.
Yeah, they're so small that the volume of each gas particle is negligible. We don't have to put it into our calculations. And how would you describe the attraction between two gas molecules? Tim?
Negligible. The attraction is so small that we can ignore it.
Right. And what do we call a gas that exactly obeys all the assumptions of the kinetic theory? Emily?
An ideal gas.
An ideal gas. And remember, in this class, we are only going to be working with ideal gases. We don't have to do any of the other crazy calculations that we talked about yesterday. So what type of proportion is a relation in which the value of one variable depends directly upon the volume of another variable? Tim?
A direct proportion.
Right, so as one thing increases, the other thing increases. So as the temperature of a gas increases, the velocity of the gas molecule is going to increase, and that would be a direct proportion. So we're going to jump right into our lesson on gas pressure, looking at these two balloons. These two balloons obviously have something very different going on, not just size. This balloon is much less inflated than this balloon, but why is that, Abby?
One has more gas in it.
Well, yes, one has more gas in it, but what's happening inside these balloons that is causing this one to be greatly expanded and this one not as inflated? And that's what we're going to learn about today. We're going to learn about gas pressures. Now, we know that gas pressures, or gas, it moves with kinetic energy. And the formula for kinetic energy is Ke equals 1/2 mass times velocity squared. Now, in this formula, we can see that the volume, or the velocity, excuse me, is much more important than the mass. And we have a problem here that's going to demonstrate that. So go ahead and take out your calculators, and we're going to do these problems to show that the velocity is much more important than the mass. So we have the kinetic energy equals 1/2 100 times 20 squared. Go ahead and put it into your calculators, and what do you get? Emily. All right, she doesn't have it yet. Go ahead, Tim. What do we have?
20,000.
20,000, correct. And what is our unit for that?
Newtons.
Correct. 20,000 newtons. Everything we get from our kinetic energy formula is going to be in newtons. So let's go ahead and flip around those units. If we do 1/2 of 20 times 100 squared, what is our answer for that? Go ahead and plug that into your calculators. And let's head on back to Emily and see what she got.
100,000 newtons.
Yes, 100,000 newtons. So from this problem, and from the answer we got, we can see that the velocity is much more important. But also think about this. If a tractor trailer was coming at you and it hit you, but it was only moving 1 meter per second, that would not hurt. But if I was to take say a pool ball and chuck it at you as hard as I could, that would hurt a lot more than getting bumped by a tractor trailer going 1 mile an hour, because the velocity is much more important than the mass. The velocity matters a great deal more than the mass does. So in these balloons, we have gas particles in both of them, and what's happening is every single time the gas particle bumps into the side of this balloon, it exerts a force, and that's what gives us a pressure. We have pressure equals force over area. So in this balloon, there's much less gas in it than in this balloon, so there's a lot less force just because there's less gas particles bumping into this balloon than there are into this balloon. So that's why this balloon is much more filled up than this balloon, just because there's so much more force going on in this balloon than inside of this balloon. Now, what if I took this balloon and I didn't tie it off? If I just blew it up and if I let it go free, what would happen? Tim?
It would probably like fly around the room.
Yeah, it would fly around the room. It would release the gas. Why do you think that is? Why won't the gas just stay in here? I blew it up in here. Why won't it just stay in here? Abby, any ideas?
Because it's elastic and it's bouncing around.
That might play some part of it, but the real answer is because there's atmospheric pressure pushing on the outside of this balloon, squeezing it, causing the gas to be forced out of the balloon. And this happens with any container. Our bodies have an internal pressure that is opposite and equal to the external atmospheric pressure that we're feeling right now. And if God hadn't created us with an internal pressure that was equal to the external pressure we'd feeling, we would deflate like this balloon. Be thankful that God thought of everything when He created us. Now, a good example of this that you can see is you ever go on an airplane, and before you get on the airplane, you suck some air out of a water bottle so that it's slightly crunched up. And then you go onto that airplane. As you climb higher and higher into the air, the atmospheric pressure is going to become less and less because you're getting higher and higher in the atmosphere. It's like you're getting higher and higher up in a pool of water. There's less air pressing on you, just as there would be less water pressing on you in a pool. So what's going to happen is that the bottle is going to start to expand because there's less pressure pushing on the outside. Now, the man that figured out how to measure atmospheric pressure, his name is Torricelli. And Torricelli created what we know as a barometer today. Go ahead and look at the bottom of page 62. You can see a good picture of barometer and also learn how to spell Torricelli's name, because that's someone you're going to want to remember. Now, what Torricelli did is he took a vial of mercury and he took that vial and turned it upside down and put it into a dish of mercury. The mercury inside the vial, it went down a little bit, but it didn't go down all the way. And the reason is because atmospheric pressure is pushing down on the mercury in that dish, which then, as it's pushing down on the mercury in the dish, it's pushing up on the mercury in the vial, and it's raising the mercury up in that vial. And that's how he determined how to measure atmospheric pressure. And what he did is he would go out and he would measure it in millimeters. Every single millimeter of mercury in there is how he would count the atmospheric pressure. So our first unit of pressure is 1 millimeter of mercury. But mercury is not the greatest indicator of pressure because mercury, it's affected by a lot of different factors, mainly temperature and how high elevation you are. The lower in elevation you are, the greater the pressure is going to be. The higher in elevation you are, the lower the pressure is going to be. So milliliters mercury, it's useful, but it's not as exact as our next unit, which is torr. And a torr, it's numerically equal to 1 millimeter of mercury, but a torr is defined exactly in newtons, so it's much more scientifically accurate than a millimeter of mercury. So because they are numerically the same, if I had 300 millimeters of mercury, that would equal 300 torr. They're numerically the same, even though the units are different. The next unit we're going to be looking at is the Pascal. Now the Pascal, which is indicated by PA, this is the SI unit of pressure. This is the unit of pressure that is used in scientific equations generally. But what's important about this is 1 Pascal is equal to 1 Newton. And 1 Newton is not a lot of pressure, so what is usually used is kilopascals, so 1,000 pascals, and that is generally what is used in our equations. And remember, the pascal is the SI unit of pressure. You're going to want to write that down in your notes. The next is ATM. ATM stands for our standard pressure. If we were to go to sea level, we would find that we would have 1 ATM, which is equal to 760 torr. That's our standard pressure. So if we're at sea level and I took out my barometer, it would read 760 torr. Now, thinking question for you. If I went to sea level, my barometer, took it out, and I measured it, and I found that it was exactly standard atmosphere, 760 torr, how many millimeters of mercury would it be? Emily?
I'm not sure.
Well, think about this. If 1 torr is equal to 1 millimeter of mercury, and I have 760 torr, how many millimeters of mercury would it have?
760?
760, exactly. They're numerically the same, even though the units are different. The next unit we have is a bar. Now, the bar is used a lot in meteorology. You can hear them, if you go watch the news, they might talk about how many bars of pressure it is today. So this is generally used in meteorology, but it's not used in scientific calculations generally. So the mercury barometer was a really good way to start us on our measuring of pressure, but because it is so influenced by environmental factors, we had to get something better. So that's where we got the aneroid barometer. Now, the aneroid barometer, it's a small airtight box that has springs in it that help you measure the atmospheric pressure. And you'll find these in airplanes and other vessels like that, where they really need to know exactly what the pressure is to be able to stabilize cabin pressure, like in an airplane or in a submarine or things like that. So remember that the aneroid barometer is what's used, is that airtight box that is used. So let's go ahead and do some quick review. What type of energy do gas molecules have? Tim?
Kinetic energy?
Correct. And what is the equation for kinetic energy? Emily?
K equals 1/2 mass times volume squared.
Yes, exactly. And what causes there to be pressure in a container filled with gas? Abby?
It's all the collisions.
Yeah, all the collisions inside, just like in our balloon. And what is the SI unit for pressure? Emily?
Pascal.
Pascal. And what is the atmospheric, or the standard atmosphere? What is standard atmosphere measured in? Tim?
Torr?
Well, how many torr?
760.
760 torr, correct. Who invented the mercury barometer? Emily?
Torricelli.
Yes. And what type of barometer senses pressure using a flexible airtight box? Abby?
The aneroid barometer.
Correct. Great job today, class. You really seem to be getting the concepts of pressure. Take out your homework pads and go ahead and write down today's homework. For today's homework, you're going to be reading page 65 to 68 up to combined gas law, volume, pressure, and temperature, and answering page 65, application 2 and 3.